The third shift at Holbrook Mill began at 11:10. Thomas Garrett pushed open the workshop door and felt the cold rush in behind him. November air, river damp and metallic. The forge had been banked hours ago, and now the building held only residual heat, the kind that clings to brick and iron but won't warm your hands. He hung his coat on the peg beneath the clock and checked the time by his pocket watch. 11:14. The factory clock read 11:14. He wound the lamp and set it on the workbench. The flame caught steadied, threw long shadows across the lathes and drill presses. Everything stood silent. The day's shift had left the place clean, chips swept, tools racked, belts slack on their pulleys. In the daytime this room roared. 30 men working metal, steam hissing through the overhead pipes, the main shaft turning with its freight of spinning leather and iron. But at night, the workshop became something else. A cavern of dark iron. A place where small sounds carried. The clock ticked. It hung on the east wall, just above the tool cabinets. A regulator clock in a walnut case, 8 feet tall, face painted white with Roman numerals in black. The pendulum swung behind glass, a brass disc catching the lamplight with each pass. Tick, tock, tick, tock. The sound filled the room the way water fills a well. Garrett opened his logbook and began the nightly inspection. Boiler pressure, holding at 15 pounds. Steam traps, clear. Condensate return, flowing. Bearing temperatures, cool. He moved through the rows of silent machines, checking oil levels, testing tensioners, noting the small imperfections that a day of hard running always left behind. A loose set screw here, a belt stretched there. Nothing urgent, nothing that couldn't wait for daylight. By midnight, he'd finished the north end of the shop. He returned to the workbench, checked his pocket watch, and glanced up at the factory clock. 12:19. His watch read 12:11. Garrett frowned. He pulled the watch closer to the lamp, tilted it, made sure he wasn't misreading the hands. No, 12:11 exactly. He looked back at the clock on the wall. 12:20 now. 8 minutes fast, in less than an hour. He stood and walked to the base of the clock, boots echoing on the wood floor. The pendulum swung steadily behind the glass door. Tick-tock, tick-tock. But the rhythm felt wrong, not dramatically wrong, not the wild racing of a broken escapement, but subtly, persistently off, like a heartbeat after climbing stairs, faster than it should be. Garrett opened the case door and touched the pendulum bob, stopping it gently. The ticking ceased. He counted to 10, released it, and watched it resume. Smooth arc, clean pivot, no binding. The escapement clicked precisely, each tooth catching and releasing in perfect mechanical sequence. He checked the weights, both hanging where they should, neither tangled nor stuck. He examined the gears by lamplight, looking for chips or wear. Nothing. He closed the case and stepped back. The clock read 12:24. His watch, 12:16. Garrett felt the cold now, properly. It seeped through the walls, through the floor, up through the soles of his boots. The building creaked as it always did. Wood settling, metal contracting, the long, slow exhalation of a structure cooling into the night. Somewhere in the darkness above, a steam pipe ticked softly as condensation dripped through it. And the clock kept gaining. By 2 in the morning, it was 15 minutes fast. By 4, 23 minutes. Garrett stopped checking. He finished his inspection, filled out his log, and left the building at dawn. When he passed beneath the clock on his way out, it showed 6:41. His pocket watch read 6:11. 30 minutes gained in a single night. He said nothing to the day foreman. What would he say? The clock's running fast at night. It sounded like exhaustion talking or drink. So he went home, slept through the afternoon, and returned that evening. The factory clock read 6:02 when he arrived. His watch, 6:02 exactly. During the day, the clock kept perfect time. The clock had been installed in 1883, purchased from the Belknap Clock Company of Syracuse for the sum of $42. It was a precision regulator, deadbeat escapement, temperature-compensated pendulum, Graham movement, the kind of clock railroads used. the kind that lost less than a second per week when properly maintained. For 3 years, it had kept perfect time. Then, sometime in late autumn of 1886, it began to accelerate at night. Not every night at first, just occasionally, an odd evening when the third shift men would notice it running a few minutes fast by morning. They'd mention it to the day crew, who would check and find nothing wrong. The clock would run true all day, lose nothing, gain nothing, tick with the stolid precision it was built for. But when darkness came and the factory quieted, it would begin to drift. By December, the pattern had become undeniable. Garrett kept a log. Every night he recorded the time shown on the factory clock against his pocket watch, a railway-grade Waltham that he had calibrated at the jeweller's just to be certain. The discrepancy grew predictably, almost mathematically. The clock would begin the night synchronized perfectly. Then somewhere around midnight it would start to gain. Slowly at first, a minute here, 2 minutes there, then faster. By the early morning hours it could be running 20, 30, even 40 minutes ahead. Come sunrise, when the day shift arrived and the building woke, when steam began flowing and the machinery started turning and 50 men filled the workshop with noise and heat, the clock would slow. By mid-morning, it matched the watch again. The workers developed theories. Samuel Prout, who ran the main engine, believed something was wrong with the pendulum suspension spring. Metal fatigue, he said. The spring weakened at night when temperatures dropped, allowing the pendulum to swing faster. But that didn't explain why the clock corrected itself during the day. James Holloway, the millwright, thought the problem was in the escapement, some microscopic wear that manifested only under certain conditions. But when he examined the mechanism with a jeweler's loupe, he found the pallets pristine, the teeth sharp, the action clean. Others blamed the cold. Thermal expansion, they said. The pendulum rod contracting at night, shortening the period, increasing the frequency. But pendulum clocks were designed to handle temperature changes. That's why the good ones used compensation rods with metals that expanded and contracted in opposite directions, cancelling out the effect. And Holbrook's clock had a mercury-compensated pendulum, the finest design available. By January, the rumors turned darker. Old Isaac Fletcher, who'd worked at the mill since before the war, mentioned that a man had died in the workshop years ago, crushed between a lathe and a grinding wheel when his apron caught in the belt drive. Maybe, Fletcher said, the ghost was still here. Maybe it wandered at night and disturbed the clock. Nobody took that seriously. But nobody could explain the clock either. The superintendent, a practical man named Holland, grew tired of the mystery. He sent for a clockmaker. Nathaniel Webb arrived on a Tuesday morning in late January, carrying a leather case of tools and an air of supreme confidence. He was a clockmaker from Albany, trained in the Swiss tradition, with a reputation for solving impossible problems. Holland had hired him for $5 and expenses to diagnose and repair the factory clock. Webb spent an hour simply observing. He stood at various positions around the workshop, listening to the clock tick, watching the pendulum swing. He noted the time on the factory clock, checked it against his own chronometer, recorded the ambient temperature with a glass thermometer. He asked questions. When was the building constructed? What kind of foundation? What ran in the basement? Were there steam lines nearby? Did the floor vibrate during the day? Then he opened the case. Webb worked with the methodical precision of a surgeon. He removed the pendulum and examined the rod under magnification, checking for hairline fractures, testing the mercury columns for proper fill level, verifying that the brass and steel tubes moved freely. He inspected the suspension spring, flexing it gently, looking for signs of crystallization or metal fatigue. Nothing. He examined the escapement next. The anchor, the escape wheel, the crutch, each component was measured, tested, compared against the original specifications. The clearances were perfect. The pallets showed no wear. The locking faces met the teeth at exactly the correct angle. Webb checked the weight lines for stretch, the gear trains for play, the mounting board for looseness. He examined the dial wheels, the motion work, the winding mechanism. Every part was exactly as it should be. By midday, he had found nothing wrong. "The clock," he announced to Holland, "is mechanically perfect." Holland frowned. "Then why does it run fast at night?" Webb spread his hands. "I don't know, but I'll stay tonight and observe." That evening, Webb returned with Garrett for the night shift. They set up a workstation beneath the clock, a table with Webb's chronometer, a thermometer, a notebook, and a good lamp. Webb checked the time. 6:38, both clocks in agreement. The temperature, 54 degrees Fahrenheit. They waited. The factory was silent, except for the clock's ticking and the occasional creak of settling timbers. Webb sat motionless, watching the pendulum swing. Garrett made his rounds, but returned every half hour to check the time. By 11 o'clock, the discrepancy had begun. Webb's chronometer, 11:04. Factory clock, 11:07. 3 minutes fast in 4.5 hours. Webb stood and examined the pendulum again. The swing looked identical to what he'd observed during the day, same amplitude, same smoothness. He checked the temperature, 46 degrees. The building had cooled 8 degrees since sunset. "The mercury compensation should handle that," he muttered. By 1 in the morning, the clock was 9 minutes fast. By 3, 18 minutes. Webb grew frustrated. He opened the case repeatedly, checking and rechecking every component. He measured the pendulum's period with a stopwatch, counting swings. It was definitely faster, completing 61 beats per minute instead of 60. But there was no mechanical reason for it. At 4 in the morning, he sat down heavily at the table. "I don't understand," he said. Garrett, standing beside him, said nothing. He'd grown used to the mystery, but seeing Webb, a master clockmaker, baffled by it made the situation feel stranger, more wrong. The clock ticked on, faster than it should, for reasons no one could name. Webb stayed 3 nights. He tried everything, adjusting the suspension, changing the pendulum length, altering the weight drop. Nothing worked. The clock ran perfectly during the day and sped up every night. He finally admitted defeat, packed his tools, and left without charging Holland for his time. "I can't fix," he said, "what I can't understand." The answer, when it finally came, arrived not as a single revelation, but as an accumulation of small observations. It began with Robert Voss, the mill's chief engineer. Voss had been listening to the clock problem for weeks with growing skepticism. Clocks didn't just run fast for no reason. If the mechanism was sound, and Webb had confirmed it was, then something external was acting on it. The question was what? One night in February, Voss came to the workshop during third shift. He brought no tools, no instruments. He simply walked the floor, paying attention to things most people ignored. The building made noise. Not the noise of running machinery that was absent at night, but quieter sounds, structural sounds. The wood frame groaned as it cooled. Nails creaked in their holes. Overhead, the steam pipes ticked rhythmically as condensation formed and dripped. And beneath it all, so faint you had to stand still to notice it, there was a vibration. Voss knelt and placed his palm flat on the floor. There, a pulse, barely perceptible but steady. It came up through the boards, through the joists, from somewhere deep in the building's bones. He followed it, moving slowly through the workshop, pausing every few feet to feel the floor. The vibration was strongest near the east wall, right where the clock hung. Voss stood and examined the wall. It was brick, 2 feet thick, tied into the building's main structure. Steam pipes ran vertically inside it, carrying condensate down from the upper floors. He pressed his ear against the brick and heard water trickling. But there was something else, a deeper sound, a resonance. He followed the wall to the basement. The basement of Holbrook Mill was a forest of iron, columns supporting the upper floors, beams carrying the weight of machinery, a maze of pipes distributing steam and returning condensate. The main boiler sat in the far corner, banked but still warm, holding pressure for the night. And beyond it, barely visible in the lamplight, A mechanical pump chugged slowly, circulating water through the heating system. Voss walked closer. The pump was a simple affair, a small steam engine driving a piston, pushing water through cast-iron pipes that ran throughout the building. It operated continuously, day and night, maintaining circulation. And every time the piston completed a stroke, it sent a pulse through the pipes. Voss placed his hand on the nearest pipe. He felt the pulse, a rhythmic throb once every 2 seconds. He followed the pipe upward. It ran vertically through the brick wall, directly behind where the factory clock hung. Back upstairs, Voss examined the clock's mounting more carefully. The case was bolted to a wooden board, which was lag-screwed into the brick wall. The brick wall carried the pipe vibrations. The vibrations transferred to the mounting board. The mounting board shook the clock case. The clock case disturbed the pendulum. Not much, not dramatically, but enough. A pendulum is exquisitely sensitive. Its period depends on length and gravity, and nothing else in theory. But in practice, even tiny disturbances can affect it. A vibrating support can couple with the pendulum's natural swing, adding energy, increasing amplitude, shortening the period. The effect is small, a fraction of a percent, but over hours it compounds. Voss suspected this was part of the answer, but only part. He spent the next week investigating other factors. Temperature was the obvious culprit. He measured carefully. The workshop cooled from 55 degrees at sunset to 42 degrees by dawn, 13 degrees. The mercury-compensated pendulum should have handled that, but Voss wondered if the compensation was perfect. He calculated. Even a 1 millimeter change in effective pendulum length would alter the period enough to gain minutes per hour. He examined the pendulum rod again. It was a tube-within-a-tube design, steel outer tube, brass in a tube, mercury reservoir at the bottom. As temperature dropped, the steel contracted downward while the brass expanded upward, keeping the center of gravity constant, theoretically. But the mercury itself was liquid. As the temperature dropped, did it redistribute? Did surface tension pull it into a slightly different configuration? A tiny change in the mercury's center of mass would shift the pendulum's effective length. Voss couldn't measure it precisely enough to know, but he suspected it contributed. Then there was magnetism. The clock's escapement was made of steel. The pendulum rod was steel and brass, and running through the wall directly behind the clock was a cluster of iron pipes carrying hot water. Iron pipes that, in the presence of temperature gradients and mechanical stress, could develop weak magnetic fields. Voss borrowed a compass and held it near the clock at various times of day. During the day, when steam flowed through the pipes and kept them hot, the compass needle showed no deflection. But at night, when the pipes cooled unevenly, hot water still circulating through cold iron, the needle twitched slightly. A magnetic field strong enough to deflect a compass was strong enough to pull on steel components. The escapement, the anchor, the pendulum crutch, all could experience tiny forces that altered their behavior. And finally, there was resonance. Voss realized the building itself was a musical instrument. The floor, the walls, the roof all had natural frequencies at which they preferred to vibrate. During the day, the noise and activity of the factory overwhelmed these subtle modes. But at night, when the building was silent, they emerged. He did a simple experiment. He walked heavily across the floor in different locations, feeling for spots where his footfalls produced a noticeable vibration. Near the center of the workshop, the floor felt solid. But along the east wall, where the clock hung, each footstep created a slight bounce, a springiness that suggested the floor joists were resonating at a frequency close to walking pace. Close to pendulum frequency. If the floor vibrated at or near the pendulum's natural frequency of 1 cycle per second, energy would couple into the pendulum. It would swing with greater amplitude, which in a real, non-ideal, pendulum actually shortens the period slightly, making the clock run fast. Voss documented everything. Vibrations from the basement pump, temperature effects on the mercury, magnetic fields from the pipes, floor resonance near the east wall. None of these factors alone would cause the clock to gain 30 minutes in a night, but together they compounded. The clock wasn't malfunctioning. It was responding to its environment. March 7th, 1887. The coldest night of the winter. Garrett arrived for third shift at 11 o'clock and felt the cold before he opened the door. Bitter cold, the kind that made the air sharp in your lungs. Inside, the workshop was barely warmer. The forge had been out all day, a Sunday, no production, and the building had been cooling for hours. The thermometer read 38 degrees. Garrett lit the lamp and checked the clock. 11:03. His watch agreed. He made his rounds quickly, wanting to keep moving to stay warm. The machines stood like frozen monuments. Ice had formed on the inside of the windows, intricate ferns of frost that glittered in the lamplight. By midnight, he noticed the clock. 11:56 on his watch. 12:04 on the factory clock. 8 minutes fast in an hour, faster than usual. Garrett stopped his rounds and stood beneath the clock, watching the pendulum. The swing looked normal, or did it? He stared until his eyes watered, trying to see any difference. The pendulum was a blur of brass, back and forth, catching the light. Tick-tock, tick-tock, tick-tock. The rhythm seemed quick, urgent. He checked the temperature again, 34 degrees. The building was still cooling. By 1 in the morning, the clock showed 1:26. Garrett's watch, 1:13. 13 minutes fast. He'd never seen it accelerate this quickly. The building groaned, wood contracting, nails pulling, joints shifting. The floor gave a sudden sharp crack that made Garrett jump. Somewhere above, a steam pipe made a metallic shriek as cold metal contracted against its mounting brackets. And beneath it all, that faint vibration. Garrett knelt and put his hand on the floor. The pulse was stronger tonight, more insistent. The cold was making everything rigid, transmitting vibrations more efficiently. The pump in the basement, the pipes in the walls, the joists under the floor, all vibrating in a complex pattern that fed energy into the building's structure. He stood and watched the clock. The pendulum swung, the gears turned, the hands advanced. 1:32. 1:34. 1:37. The clock was racing now. Garrett could see the minute hand moving, a smooth, continuous creep rather than the minute-by-minute jumps a normal clock made. The escapement was clicking so fast it produced a sustained hum instead of distinct ticks. Garrett felt something close to fear. This wasn't mechanical failure. This was something else. The clock was responding to forces he couldn't see, couldn't control. The building was doing something to it, pushing it, driving it. By 2 in the morning, the clock read 2:47. 47 minutes fast. The temperature had dropped to 31 degrees. The windows were sheets of ice. The metal tools felt like they would burn your skin if you touched them. And the building was singing, a low, almost subsonic moan as every component contracted at once. Pipes groaned in the walls. Beams creaked overhead. The floor vibrated continuously now, a shiver that ran through the whole structure. Garrett stood motionless, listening. The clock ticked faster. 3:01, it read. His watch, 2:17. And then, without warning, everything stopped. Not the clock, the building. The groaning ceased. The vibration faded. The pressure that had been building all night suddenly released. Garrett felt it in his chest, a relaxation like exhaling after holding your breath. The clock continued to tick, but the frantic quality was gone. The rhythm slowed. The minute hand's continuous creep became discrete jumps again. 1 minute, then another, then another. By 3 in the morning, real time, the clock was stable again. Still 44 minutes fast, but no longer accelerating. Garrett checked the temperature, 29 degrees. The building had reached thermal equilibrium with the outside air. It wasn't cooling anymore. It wasn't contracting. The forces that had been driving the clock had dissipated. He sat at the workbench until dawn, watching. The clock gained no more time. When the day shift arrived, he showed them the discrepancy. 46 minutes. They didn't believe him until they saw his log. Holland called a meeting. The factory clock had become more than a curiosity, it was a problem. Men were showing up for shifts at the wrong times. Production schedules were confused, and the workers were spooked. Some refused to work nights, claiming the building was haunted or cursed. Holland wanted answers, real answers. He hired Voss to conduct a formal investigation with a budget for instruments and assistants. Voss recruited 2 other engineers, Marcus Holt from the machine works and David Chen, a surveyor with experience in structural analysis. They spent a week mapping the building. Holt measured vibration frequencies at dozens of points throughout the factory, using a device of his own invention, a tuning fork mounted on a pivot with a stylus that drew patterns on smoked glass. He catalogued the building's natural modes. The floor vibrated at 0.8 Hz in some locations, 1.1 Hz in others. The walls had their own frequencies. The roof had its own. Everything coupled together into a complex harmonic landscape. Chen surveyed the foundation, looking for differential settlement. The building had been constructed on soft ground near the river, and he suspected the east side might be sinking slightly, creating stress in the structure that would manifest as vibrations. His measurements confirmed it. The east wall had settled 2 inches more than the west wall over the building's 15-year life. And Voss focused on the clock itself. He installed a second regulator clock on the opposite wall as a control. Same model, same manufacturer, but positioned away from the steam pipes and mounted on a section of floor that showed minimal vibration. Then he instrumented both clocks with sensors, thermocouples to measure temperature gradients, magnetic field detectors made from wire coils, accelerometers fashioned from delicate springs and pointers. They gathered data for 2 weeks. The results were striking. The control clock kept perfect time, day and night. It gained less than 5 seconds per week, exactly as designed. But the original clock, the one on the east wall, continued to accelerate every night. Voss correlated the clock's behavior with environmental factors. The data showed clear patterns. Temperature was critical. On nights when the building cooled more than 10 degrees, the clock accelerated dramatically. On milder nights, the effect was subtle. The mercury pendulum's compensation wasn't perfect. It lagged behind the temperature change, creating a transient period where the effective pendulum length shortened. Vibration mattered most. The magnetic field sensors showed weak fields developing in the steam pipes at night, but Holt's vibration measurements were the key finding. The floor beneath the clock vibrated at 1.1 Hz when the basement pump was running, exactly 10% faster than the pendulum's natural frequency of 1 Hz. This created a phenomenon called parametric resonance. The floor's motion coupled with the pendulum, pumping energy into it, increasing its amplitude and shortening its period. During the day, the vibrations were damped by human activity. Footsteps, machinery, steam flow created random noise that disrupted the resonance. At night, the pump's regular pulse dominated, and the coupling was strong. The magnetic fields contributed, but only slightly. Chen's structural analysis showed that temperature stress in the building altered its vibrational characteristics. As the building cooled, joints tightened, stiffness increased, natural frequencies shifted, creating conditions that enhanced the resonance effect. Everything Voss had suspected was confirmed. The clock wasn't broken. It was responding to a perfect storm of environmental factors that only occurred at night. Rapid cooling, pendulum compensation, lag, right arrow shortened period. Building contraction, right arrow, enhanced vibration transmission, right arrow parametric resonance. Differential foundation settlement, structural stress, altered floor frequencies. Steam pipe fields right arrow, minor magnetic interference with escapement. Pump vibration, right arrow floor resonance, right arrow energy, coupling to pendulum. No single factor was decisive, but together they created a feedback loop that drove the clock faster and faster until the building reached thermal equilibrium. Voss presented his findings to Holland with a written report and recommendations. The clock is functioning as designed, he concluded. The problem is where we put it. Holland read the report twice, frowning. So what do we do? Move it, Voss said. Mount it on the west wall where the floor is solid and the pipes don't run. Or better yet, build a standalone clock tower outside the main building. That would cost money. Less than the confusion is costing us now. Holland considered, what if we just reset it every morning? Voss shrugged. You could, but you'd be fighting the building every night. In April of 1887, the factory clock was moved. They mounted it in the front office, on an interior wall with no steam pipes nearby, on a floor that sat on solid footings. It hung there for the next 40 years and never again ran fast at night. But the story didn't end there. The engineers' investigation of the clock problem had revealed something deeper. The factory was not a static structure. It was a living system, responsive to forces both obvious and hidden. Temperature, vibration, settlement, resonance, all interacted in ways that could affect even the most precise instruments. This realization changed how factories were designed. Engineers began paying attention to where they placed sensitive equipment. They isolated clocks and other instruments from vibration sources. They studied how buildings moved and breathed with daily temperature cycles. They learned that mechanical precision wasn't enough. You had to consider the environment. The Holbrook Mills clock became something of a legend in engineering circles. Papers were published about it. Students studied it as a case in fluid structure interaction and parametric resonance. It was an early lesson in systems thinking, that everything in a complex environment affects everything else. And for the workers who had witnessed the clock's nightly acceleration, the memory stayed vivid. They'd seen time itself become unreliable, not through mechanical failure, but through the subtle tyranny of hidden forces. The building they worked in every day had revealed itself as something more than brick and iron. It was an instrument, as finely tuned in its own way as the clock that hung on its wall. Years later, when the mill was demolished and replaced with a modern plant, someone salvaged the clock. It sits now in a museum, behind glass, its pendulum still swinging. A small placard tells the story, though simplified, stripped of technical detail, reduced to an anecdote about a clock that ran fast at night. But those who understand mechanical systems see something more when they look at it. They see a machine that told the truth about its environment, a clock that didn't lie about the forces acting on it, even when those forces were invisible. It responded honestly to vibration, to temperature, to resonance, to all the hidden dynamics of the building that contained it. In a sense, it was a more accurate instrument than anyone realized. It wasn't measuring time. It was measuring the building itself. And every night, when the factory fell silent, and the structure began to cool and contract and resonate with the pulse of distant machinery, the clock faithfully recorded those changes. It translated them into the only language it knew, the movement of hands across a face, the ticking of an escapement, the swing of a pendulum. It was never broken. It was simply telling a different story than the one people expected. The factory existed as an ecosystem of forces, steam pressure and mechanical load, thermal expansion and acoustic resonance, gravity and inertia and magnetic fields. Every machine, every beam, every pipe was connected to every other through paths of energy and stress. Nothing operated in isolation. Nothing could be understood alone. The clock taught them that. And in the larger history of industrial engineering, it stands as a reminder. Precision is not just a property of the instrument, it's a property of the system. You can build the finest clock in the world, but if you place it in an environment it wasn't designed for, it will fail. Not through any fault of its own, but because the world acts on it in ways you didn't anticipate. The engineers who solved the mystery understood this. They traced the pathways of vibration through the building's bones. They measured temperature gradients and magnetic fields. They mapped resonance frequencies and structural stress. They saw the factory not as a collection of separate components, but as a unified whole, a machine made of machines, all interacting. And when they moved the clock, they weren't just solving a practical problem. They were acknowledging a fundamental truth about how things work in the real world. Nothing exists in isolation. Everything affects everything else. And sometimes, the most precise instrument you have is the one that shows you what you weren't looking for. The Holbrook clock ran faster at night because the night changed everything. Temperature dropped. Vibrations propagated. The building contracted and resonated and hummed with forces that were invisible during the day. And the clock, sensitive, responsive, honest, recorded all of it. It was never wrong. It was measuring what was really there. The factory at night was a different place than the factory during the day, not metaphorically, but physically, mechanically, measurably different. The clock knew that. The engineers eventually learned it, and the workers who watched time slip away in the darkness understood, even if they couldn't explain it, that the building held secrets. Now, more than a century later, we design factories differently. We isolate sensitive equipment. We control environments. We understand systems dynamics in ways the Holbrook engineers could only glimpse. But we can still learn from their clock. It reminds us to pay attention to what seems impossible, to investigate what appears broken, to look for hidden forces when obvious explanations fail. And most of all, it reminds us that the world is more interconnected than we usually notice, that even something as simple as keeping time depends on everything around it. The factory clock ran faster at night, not because it was broken, but because the night was different, and the clock was honest enough to show it.